We are a species that refuses to stay put. From freezing poles to the deepest ocean trenches, humans have a long history of pushing into the most extreme, inhospitable environments we can find. The ultimate test of that drive happened in 1969. We left our planetary cradle entirely, surviving the vacuum of space to leave boot prints on a world that wasn't ours. The engineering required for that trip was staggering. We navigated 240,000 miles of a deadly vacuum, relying on computers with a fraction of the processing power of a modern smartphone. That lunar triumph proved our capability to cross the void. Now, half a century later, that same instinct has us looking past the moon, scanning the sky for the next logical destination. Our modern telescopes have pinpointed a compelling target, our nearest stellar neighbor, a planet known as Proxima Centauri b. Its rocky composition and Earth-like mass make it a legitimate twin Earth, a solid world rather than a ball of toxic gas. This diagram maps out the habitable zone. It shows the orbital distance from a star where a planet is neither too hot nor too cold. Proxima b sits right inside this green life-sustaining boundary, meaning it theoretically could support liquid water. So we have a habitable-looking twin sitting just 4 light-years away. It is practically next door in cosmic terms. Yet, despite being so close, it remains entirely out of our reach. The problem starts with the staggering scale of the universe. A trip to the moon is a 240,000-mile sprint. Proxima Centauri b is 4.24 light-years away. This graph visualizes the difference. If we boarded an Apollo-era spacecraft traveling at its historical top speed, it wouldn't take days or weeks to get there. It would take nearly 100,000 years of continuous flight to reach Proxima b. To go faster, we need propulsion. But our current workhorse engines are chemical rockets. These rely on combustion, meaning they require immense, heavy fuel payloads just to generate the raw power needed to escape Earth's gravity. Chemical propulsion works for our local solar system, but when you factor in the fuel-to-weight limitations, the math shows these engines are inadequate for crossing the trillions of miles of interstellar space. To cross that void within a single human lifetime, a vessel would need to travel at a significant fraction of the speed of light. This chart shows the mass-energy equivalence problem. As a spacecraft accelerates toward light speed, its mass increases. Pushing a heavier object demands exponentially more energy to continue accelerating, eventually requiring an infinite amount of power. Physicists propose workarounds to bypass this limit, like antimatter drives or vast laser-propelled sails, but those only work for microscopic probes. Watch the energy curve when we increase payload mass. Scaled up to push a vessel with human life support, the engineering requirements collapse entirely. Our imaginations and our theoretical mathematics have outpaced our engineering. The physical laws of the universe act as a hard barrier, guarding the exit to our solar system. Even if we built a massive, multi-generational arc that traveled slower, we face a different wall. We have to look past the limits of the ship and consider the biological realities of the human payload. Leaving the protective magnetic bubble of our solar system exposes a ship to the primary threat of deep space, constant bombardment by high-energy cosmic radiation. Then there is the mechanical threat. At relativistic speeds, a collision with a microscopic piece of space dust carries the kinetic energy of a detonating bomb. Internally, the body degrades in zero gravity. Over decades of travel, astronauts suffer rapid bone density loss, severe muscle atrophy, and systemic weakness. If the physics of speed and propulsion were solved tomorrow, we are still stuck. The baseline frailty of the human body itself represents an insurmountable hurdle for a deep space odyssey. We are bound by the truths of physics, engineering, and biology. Proxima Centauri b is an inaccessible mirage for current human civilization. We have reached a point where our observation has entirely outpaced our reach. We can map the shorelines of a cosmic ocean we are not yet equipped to cross. The realization of our cosmic isolation directs our attention back to our immediate reality and the day-to-day existence we share right now. Knowing we cannot simply relocate or escape to a twin Earth increases the intrinsic value and the fragility of our current home. Until we can invent a way to break the uncompromising laws of physics, the only accessible Earth we will ever have is the one beneath our feet.